Welcome back to the deep dive. So today, we're going to do something a little different.
Oh, yeah.
We're going to strip away the marketing fluff. Usually when we talk about cloud computing, we use these very ethereal, soft metaphors. It's serverless, it's floating, it's omnipresent.
Right. It's just magic. You push a button, pay your subscription, and poof, the application exists.
Exactly. And it's a nice image, but if you're actually responsible for keeping the lights on, if you're an admin, an architect, or hey, maybe you're studying for the AZ-104 exam, you know that data doesn't actually float.
No.
It flows. It travels through pipes, it hits walls, and if you aren't careful, it gets stopped at gates you didn't even know were there.
And if you don't understand the plumbing, you are going to have a very, very bad time. I mean, you can have the best code in the world, the most optimized database queries.
Right.
But if the packets can't get from point A to point B because of a misconfigured route or a blocked port, your application is down, period.
So today we're looking at that invisible infrastructure. We're doing a deep dive into Microsoft's configuration documentation for Azure Virtual Networks, or VNets. And the mission today is to go from I store files in the cloud to I run a secure enterprise-grade network in the cloud.
Which, to be clear, is a massive leap in complexity.
It is. So let's start at the absolute bottom, the VNet itself. The documentation calls it the fundamental building block of your private network. But let's be real for a second. Is a VNet just a VLAN in the sky? Is it just a cable?
In a way, yes, but that really undersells it. Think of a VNet as a logical isolation boundary. When you spin up a VNet, you're essentially carving out your own private slice of the massive shared public cloud.
So even though my data is sitting on the same physical hardware in a Microsoft data center as, I don't know, a competitor's data,
Yeah.
logically, we're on different planets.
Exactly. It's your own private IP address space. You control the routing, you control DNS, you control the security policies. It's basically an extension of your own data center just running on Microsoft's hardware.
And the business case the docs make for this is pretty standard, So you stop paying for AC units, you stop buying diesel for backup generators. But they really harp on hybrid scenarios. Why is the VNet so critical for hybrid specifically?
Because almost nobody moves to the cloud overnight. You're going to have legacy SQL servers sitting in your basement for the next 5 years.
Or 10.
Or 10. A VNet allows you to connect that basement to Azure securely. You can set up what's called a site-to-site VPN using ITSEC.
So to the server in the basement, the Azure VNet just looks like another branch office.
Precisely. It routes traffic over a secure tunnel right through the internet. Or, if you've got the budget, you use ExpressRoute for a dedicated private line. But either way, the VNet is the landing zone on the Azure side. Without it, you have nowhere to connect to.
Okay, so we've bought our plot of land. We have this big address space in the cloud. Now, if I just dump all my VMs, my databases, my load balancers into this one big VNet, am I doing it right?
You are. Technically, you can do it, but architecturally, it's a disaster. That's a flat network. If an attacker compromises one web server, they can just move laterally to everything.
Your database, your domain controller.
It's all just sitting right there next to the compromised box.
So this is where we get into subnets.
Right. Subnets are how we organize the chaos. You take that massive CIDR block you assign to the VNet, say a 16, and you slice it up into smaller chunks.
CIDR being classless interdomain routing. I always have to stop and remind myself what that acronym stands for.
Yes, the slash notation, 24, 26, and so on. It just defines the size of the network.
I want to pause on this because the docs highlight three main benefits of subnets: security, performance, and management. Security, I get, we can put walls between them, but how does it help performance?
Well, it limits broadcast domains mostly, but honestly, in the cloud, the biggest performance win is really logical grouping. You put all your chatty front-end servers in one subnet so their traffic stays local, and your heavy back-end databases in another. It just makes all your routing policies much, much cleaner.
Okay, so we're slicing up a pie.
Yeah.
But here is the part of the documentation that I think trips up every single person the first time they do this. The rule of 5.
Oh, the missing IPs. Yes, this is a classic gotcha.
Walk us through this. So in traditional on-prem networking, if I have a subnet, I lose the network address and the broadcast address. So I lose 2 IPs.
Right, the first one and the last one.
But Azure takes 5.
5. Every single time, in every single subnet you create.
Why? I mean, what is it doing with them?
Okay, let's break it down. Let's use a standard 192.168.1.024. So you have 256 addresses, theoretically.
Okay, 256.
First you have .0, that's the network address, standard stuff, that's gone.
Check, that's one.
Then the last one, .255, that's the broadcast address. Now, here's a fun little fact from the docs.
Yeah.
Azure doesn't actually support broadcast networking.
Wait, really? So I can't send a hello to everyone in the network?
Nope. Azure's software-defined networking, it blocks it. It just creates too much noise on a public cloud. But, and this is the key part, they still reserve the .255 address just to stay compliant with standard networking protocols.
Okay, so that's 2 gone. Where are the other 3?
So point 1 is your default gateway. That's the virtual router that lets your VMs talk to the rest of the world.
Makes sense. That's 3.
And here is the Azure tags. Point 2 and point 3. These are reserved to map Azure DNS IPs to the VNet space.
2 whole addresses just for DNS mapping.
It's for redundancy and for the underlying fabric management, but really the why matters less than the math.
The math being 256 minus 5 is 251.
Exactly. And this sounds like a small detail, I know, until you're migrating a legacy cluster. I have seen this happen. A company creates a migration plan. They have a cluster of, say, 252 appliances that need to be in the same subnet for heartbeat monitoring.
And so they provision a 24 subnet.
They provision a 24. They think they have 254 usable IPs because that's what they've had in their on-prem Cisco gear for 20 years. They start the script. The 252nd VM fails to deploy.
Because they only had 251.
And now they have to tear down the entire subnet, resize it, and redeploy everything. All because they forgot the rule of 5.
That is just
Yeah.
painful. So the takeaway here for you listening, always calculate your required IP count plus 5.
Always. And honestly, give yourself a buffer. Don't try to fit perfectly. Storage is cheap, and private IP space is essentially free. Use a bigger subnet if you can. Don't paint yourself into a corner.
Speaking of IP space, let's pivot to the addresses themselves. The sources make a really sharp distinction between private IPs and public IPs.
Right. Private IPs are what we were just talking about, communication inside your bubble. They are totally invisible to the internet. Public IPs, though, they're the billboard. They face the world.
And there are 2 ways these get assigned. Static
Right.
and dynamic. The docs say dynamic is the default.
Yeah. In the cloud, we treat servers like cattle, not pets, right? So usually, we don't care what the IP is. You spin up a VM, Azure grabs the next available 1.10.1.11 and gives it to you. If you stop that VM and start it a week later, it might come back as like 0.55.
Which is fine for a web server in a pool. But the sources list specific scenarios where you absolutely must use static.
The big one is domain controllers. If you're running Active Directory in Azure, your domain controller is the source of truth. If its address changes, nobody can log in.
That seems
Yes.
critical.
Yeah. Also, think about firewall rules. If your on-premise firewall says only allow traffic from 10 byte 0.5 and you leave that Azure VM as dynamic, you reboot, it gets a new IP, and poof, the tunnel drops.
And SSL certificates.
Same thing. If you bind a certificate to an IP address and that IP changes, the browser screams unsafe website at all your users.
Okay, now on the topic of public IPs, there was a warning in the text about SKUs, standard versus basic. I feel like basic usually implies good enough for testing, but the doc suggests basic implies obsolete.
It's worse than obsolete. It's expiring. And this is a very time-sensitive point for anyone listening. Microsoft is retiring the basic SKU public IP on September 30, 2025.
That is effectively tomorrow in enterprise planning terms.
It is. If you have basic IPs in your subscription, you need a plan to upgrade them to standard.
What's the actual difference? Why force the upgrade? Is it just a cash grab?
It's really about resilience. Basic IPs are, they're open by default. They don't have the same security integration. But more importantly, basic IPs do not support availability zones.
Okay. Let's unpack that. Availability zones are physically separate data centers within a single region, right?
Exactly. So if Zone 1 loses power, Zone 2 is still up. But if you use a basic public IP, that IP is tied to a single spot. If that spot goes down, your IP goes down with it.
So if I want my application to survive a data center failure by spanning across zones, I literally cannot use a basic IP.
Correct. If you're building for high availability, which you should be, you must use standard SKUs. They are zone redundant by default.
There was one other weird quirk in the IP section regarding IPv6. We mostly live in an IPv4 world, but IPv6 is, lurking.
It's always lurking. Azure supports it, but the implementation is specific. You can't just slap a public IPv6 address onto a VM's network card like you can with IPv4.
You can?
No. The documentation says explicitly that public IPv6 addresses can only be attached to load balancers.
So if I just want a standalone server accessible via IPv6 directly,
You have to put a load balancer in front of it. It kind of forces you into a slightly more complex, but probably better, architecture. It's a good gotcha for the exam or for any design review.
Okay, let's move up the stack. We have the VNet, the subnets, the IPs. Now we need to secure it. This brings us to the NSG, the Network Security Group,
The bouncer.
the bouncer. But I want to clarify something. Is it a smart bouncer or a dumb bouncer? Because, standard firewalls act differently depending on the generation.
It's a stateful bouncer.
Yeah.
And that's a really important distinction.
Unpack that for me.
Stateful.
It means the NSG remembers what conversations are happening. So if I allow traffic in, the NSG is smart enough to automatically allow the return traffic out. I don't have to write two separate rules.
So if I say, allow port 80 inbound for web traffic, I don't need a second rule saying, allow the web server to reply on a random high port. Exactly. The response packets going back to the user are automatically permitted because they're part of the same state, the same conversation.
That saves a lot of configuration headaches.
A huge amount. And the way you apply them is also really efficient. You don't usually put an NSG on every single VM. You associate the NSG with the subnet.
So it's a blanket policy.
Exactly. I create a web subnet-NSG. I say allow HTTP and HTTPS. I attach it to the front-end subnet. Now, any VM I drop into that subnet automatically inherits those rules. It's, secure by default.
But what if I want to get more complex? The docs talk about routing and NVA's network virtual appliances. When do I need those?
Yeah.
Because Azure routes traffic automatically between subnets.
Yeah, right. It does. By default, every subnet in a VNet can talk to every other subnet. It's wide open internally.
Which might be a bad thing.
Which is often a very bad thing. Let's say you have a strict compliance requirement, PCI or HIPAA. You might need to inspect every packet that goes from your web server to your database to make sure there's no SQL injection happening internally.
And Azure's default router isn't going to do that kind of inspection.
No, it just passes a packet like a relay race.
Yeah.
So what you do is you create a user-defined route, a UDR. You tell the subnet, hey, if you want to talk to the database, don't go direct. You have to go to this IP address first.
And that IP is my virtual firewall.
Exactly. That's your NVA. It could be an Azure firewall or a virtual Palo Alto or a Cisco appliance from the marketplace. It acts as a mandatory checkpoint.
I want to visualize this because the documentation includes this exercise scenario that ties all this together. They call it the hub and spoke topology.
This is the classic Azure architecture. If you learn one pattern, learn this one.
Okay, so paint the picture for us. We've got a wheel.
Right. You have the hub. That's a VNet. And you can think of the hub as your headquarters. It holds all the shared stuff. Your VPN gateway to on-prem, your Azure firewall, maybe your domain controllers.
The expensive stuff you don't want to buy twice.
Exactly. Then you have the spokes. These are other separate VNets that hold your actual applications. Maybe Spoke A is the HR app, Spoke B is finance.
And how do they connect to each other?
VNet peering. This is a key term. You peer the Spoke VNet to the hub VNet.
Is peering just a VPN?
No, and that's a crucial distinction. A VPN encrypts traffic and sends it over a tunnel, which adds overhead, it adds latency. Peering uses Microsoft's private backbone network to effectively merge the two VNets into one. It's super low latency, a high bandwidth. It's like they're plugged into the same switch.
So in this scenario, if I'm a user on the internet trying to get to the HR app,
You'd hit the public IP of the firewall in the hub. The firewall scans the traffic. It says, okay, you're clean. It then routes you across the peering link to the Spoke VNet.
and inside that spoke VNet, we've got our subnets.
Right. The exercise describes a front-end subnet and a back-end subnet. The traffic hits the web server in the front end.
And then that web server needs data.
So it talks to the back-end subnet where the SQL database lives. But, and here is the security magic, the back-end subnet has an NSG that says, I will only accept traffic from the front-end subnet.
So if I manage to hack the firewall somehow, and I try to talk directly to the database,
Blocked.
if I try to access the database from the public internet,
Blocked. It doesn't even have a public IP.
but wait, the docs also mention private link for databases.
Yeah.
How does that fit in? Because Azure SQL is a Pi service platform as a service. It doesn't usually live inside of VNet, does it?
Historically, no. Azure SQL used to just sit on a public endpoint. You'd secure it with a firewall, but technically its front door was on the public internet.
Which keeps chief information security officers awake at night.
Correct. Private link completely changes the game. It takes that Azure SQL service and it projects it into your subnet. It gives the database a private internal IP address from your own VNet range.
So the traffic never even leaves the VNet.
Never. It goes from your web server to the private link IP straight to the database, all over the Microsoft backbone. It is completely dark to the public internet.
That seems like the absolute gold standard for security.
It is. If you're building today, you should be using private links for all your PaaS services.
So we've built a fortress. We have hubs, spokes, peering, subnets, NSGs, and private links. It feels like we have covered the entire map.
We've covered the plumbing.
Yeah.
And that really is the takeaway here. You can't just put it in the cloud. You have to architect the flow.
It brings me to a final thought I had while I was reading the section on NSGs. And it's kind of a provocative question for our listeners.
Okay, let's hear it.
The text explicitly says that a network security group can be associated with 0 or 1 subnets.
0 or 1, right.
Which implies that 0 is a valid configuration.
And it is.
So Azure will happily let me create a subnet, fill it with my most sensitive servers, and attach no security rules to it whatsoever.
It absolutely will. It won't even show you a warning banner.
But why? If security is job one, why allow the door to be left off its hinges?
Well, it goes back to that philosophy of the cloud. Flexibility versus guardrails. Azure assumes you are the architect. Maybe you want it open for some reason. Maybe you're using a third-party firewall and you don't want NSGs interfering.
So it respects your decision, even if your decision is objectively terrible.
Exactly. It puts the onus entirely on you. There is no safety net that says, are you sure you want to expose this database to the world? You have to build that net yourself.
That is a terrifying, but also kind of empowering thought. You are the architect.
You are.
So here's the challenge for our listener today. Go look at your Azure portal. Look at your VNets.
Check your math.
Ask yourself, did I account for the rule of 5? Or is my subnet about to run out of space? And are my public IPs basic or standard?
And please, for the love of all that is holy, check if you have any subnets with 0 NSGs attached.
If you do, you might want to fix that before you go to lunch.
Definitely before lunch.
Thank you for diving deep with us into the invisible plumbing of Azure. It's not magic, it's engineering. We'll see you on the next deep dive.
See you then.